Hello students. So this particular question was asked from the Power Electronics section in your GATE 2024 EE. Okay, in this question they are asking that if the following switching devices have the similar power rating, which one of them is the fastest? SCR, GTO, IGBT or power MOSFET? So as we have discussed in the class, I told you that the power MOSFET has got the highest switching performance. That means its switching frequency is very high compared to SCR, GTO or IGBT. Okay, and the reason for this is that power MOSFET is a majority carrier device. Power MOSFET, it is a majority carrier device and it is unipolar. That means only the electrons are responsible for conduction here. Okay, and that is the reason it is fastest. Okay, because only out of electron and holes, only electrons are responsible for conduction. So power MOSFET is the correct answer here. Hello students. So this particular question was asked from the power electronics section in your GATE 24 EE. Okay, in this question they are asking that a single phase Triac based AC voltage controller feeds a series RL load. The input AC supply is 230 volt. And this is a question of AC voltage regulator. Although it was not included in the syllabus, but still they have asked it for 1 mark question. Okay, so the students have challenged this particular question because this was not in the part of the syllabus. Okay, AC voltage controller and the cyclo converter were removed from the syllabus, but still they have asked it. Okay, so what they are asking here, although it is a very simple question, okay, the value of R and L they have given. So the R is 10 ohm and L is 18.37 millihenry. So they have a RL load connected here. They're asking for the minimum triggering angle of the Triac to obtain the controllable output voltage. So we know that the minimum triggering angle alpha minimum is equal to tan inverse omega L by R. Okay, so this particular part is the minimum triggering angle to obtain the output voltage. Because if the angle, if the triggering angle is less than this, you will not be able to obtain the output. So here, if you see, omega, we know that it is 2 pi f, right? And f is given as 50 hertz. So 2 pi f will become 100 pi. L, the value of L is 18.37. So I can write it as 0.01837 Henry. So 0.01837 divided by R. R is 10 ohm. Okay. So what I'll get after solving this 100 pi into this divided by 10, then taking tan inverse, you'll get the alpha minimum equivalent to 30 degree. Okay, so option B is the correct answer here. Hello students, so this particular question was asked from the power electronics section in your gate 24 double E part. Okay, in this question they are asking that a force commutated thyristerized step down chopper is shown in the figure. Okay, so it is a step down chopper because the switch is here and this is your diode. It is a freewheeling diode, right? And assume that the capacitor is initially charged to 50 volt. So this capacitor is charged to 50 volt. Okay, it is charged to the supply voltage with the polarity shown in the figure. With this polarity, your capacitor is getting charged. The load current IL can be assumed to be continuous at 10 ampere. So here, this is the value of the output current or the load current, which is constant. And why it is constant? Because of this freewheeling diode. Okay, and because of the continuous conduction. Okay, so they have asked the continuous conduction case, and we have discussed the class B and class D chopper by assuming continuous conduction only. Okay, then they are asking that the main thyristor is on and the auxiliary thyristor is off. This auxiliary thyristor is off. The turn of time available to this thyristor in microsecond. Oh, they have asked for the circuit turn of time in microsecond. When TA is triggered, auxiliary thyristor is triggered. So when the auxiliary thyristor is triggered, first of all, it is a voltage commutated chopper. Because in current commutated chopper, you will get the LC oscillating circuit. But here, capacitor is connected here. Okay, and diode is connected here. But in the class B chopper, you know that, or in the current commutated chopper, this particular part will be connected with L and the diode will be connected here. Okay, so it is a voltage commutated chopper. And the circuit turn of time formula I have already given you after discussing the different modes and the waveform. Okay, so the formula was TCM is equal to CVS by I naught. So the capacitor value is already given 10 microfarad. Okay, VS is 50 volt and I naught is 10 ampere. So this will come in microsecond because capacitor was in microfarad. So 500 by 10, it will give you 50 microsecond. Okay. Hello students. So this particular question was asked from the power electronics section in your gate 24 double E part. In this question, they are asking that a single phase half controlled bridge converter supplies an inductive load with a ripple free load current. So they have given you that it is a semi converter. Okay, that is a half controlled converter. Half controlled converter, not fully controlled. Okay, and they have also given that it is connected with the RL load. Inductive load means RL load, not a purely inductive load, with a ripple free load current. That means I naught is constant and it is a case of continuous conduction. Okay, continuous conduction. They're asking that they're telling that a triggering angle is 60 degree. So alpha is given as 60 degree here, triggering angle. They're asking the ratio of RMS value of the fundamental component to the input current to the RMS value of the output current of the bridge. Okay, so it is a very easy question because we already know the harmonic analysis of a semi converter. I told you that the fundamental RMS source current was equal to 2 root 2 by pi I naught cos alpha by 2, and the total RMS input current is equal to I naught under root pi minus alpha upon pi. Yes or no? So they have asked us the ratio of this. Okay, so you can see that if I just find out the ratio, IS1 RMS by IS RMS, that is fundamental RMS source current and this is the total source current. Okay, so this would be 2 root 2 by pi I naught cos alpha by 2, and this is I naught under root pi minus alpha upon pi. I naught will get cancelled, and this will become 2 root 2 by pi cos alpha is 60 degrees. So cos 60 by 2 is cos 30. Cos 30 is root 3 by 2, and under root pi will come here, and this will become under root pi minus pi by 3. So pi minus pi by 3 will become 2 pi by 3. So 2 pi by 3. So if you solve this, you can see that this will be under root pi. Okay, and under root pi, 2 and 2 will get cancelled here. Okay, under root 3 and under root 3 will become, because this is under root 3, so this part will go in the numerator, so it will become 3, and under root 2 here and under root 2 here, under root 2 will get cancelled, and under root pi into under root pi will become pi. So it will be 3 by pi, which is coming as 0.95. 0.95. So it was the value of total harmonic distortion for this three-phase converter, right? Three-phase converter. So at alpha equal to 60 degree, okay, for this semi converter, I am getting the fundamental value of this RMS current by total current ratio as 0.95. So this was the ratio they were asking for. So the answer is 0.95. Hello students. So this particular question was asked from the power electronics section in your gate 24EE, right? In this particular question, they are asking that a single phase full bridge voltage source converter feeds a purely inductive load. The inverter output voltage is a square wave, that is 180 degree conduction mode. The fundamental frequency of the output voltage is 50 Hz. If the DC input voltage of the inverter is 100 volt and the value of load inductance is 20 millihenry, then the peak to peak load current will be peak to peak load current they are asking. Okay, so it is a single phase full bridge inverter. Okay, and the load is a purely inductive load, pure L load. Okay, pure inductive load, and the inverter output voltage is a square wave with 180 degree. Okay, the fundamental frequency, so frequency they have given as 50 Hz, and the DC input voltage of the inverter, that is Vs, is given as 100 volt. Okay, and the value of load inductance is 20 millihenry. So I know that for a purely inductive load, my load current would be linearly rising, okay, from minus I naught to plus I naught, right? I have already shown you this, that the output voltage will be independent of load. Okay, it will be plus Vs for T by 2 and the minus Vs for T by 2. Your output voltage is independent of load. Okay, so this is your Vs, and that is 100 volt, and this is Vs, and that is minus 100 volt. Okay, and this is the waveform for output voltage. Okay, so output voltage will be Vs for T by 2, and this will be total time period T. So the output voltage will remain a square wave only. It is independent of load. But my output current or the load current will be changing with respect to load. Okay, that is for different load. If I connect a RL load, it will be some other shape. Okay, shape of the waveform will be different. If it is a RLC load, shape of the waveform will be different. If it is a RL load, then also shape of the waveform will be different. Now, what I'll do is I'll draw the output current. So output current or the load current will look like this. Okay, it will go from minus I naught to plus I naught. and plus I naught to minus I naught. So if you see here, this is plus I naught. This particular part, if you see, or let me show it like this. Plus I naught minus I naught. Okay. This is minus I naught. This is plus I naught. And this is minus I naught. So you can see that Vs is equal to VL. Okay. Because the out here, when the switch is on, you know that for a full bridge converter, when the switch is on, Vs is equal to V naught, and that is given as 100 volt, right? And V naught is nothing but VL. So Vs will be equal to VL. And you know that change of rate of change of current. Okay. L into rate of change of current. So this will be L. How it is changing? It is going from minus I naught to plus I naught in this particular time period. Yes or no? So I can write 2 I naught is the change in the current in the time period T by 2. That is 100 volt. So from here I can calculate the value of 2 I naught. So that will be 100 T by 4 L. 100 T by 4, no, not 4L, 2L. Because I am calculating 2 I naught, okay, not I naught. So you know that the peak to peak load current is nothing but your ripple current, okay, and the ripple current is given as 2 I naught, okay, because the change is from minus I naught to plus I naught, not from 0 to I naught. If the change would be from 0 to I naught, then you will say the ripple current is I naught, but here the ripple current is 2 I naught. So 100, I have already got the value of 2 I naught. It is 100. So I can write down it as 100 by 2 F L. You just put all the values. So 100 by 2. So 2 I naught will be 100 by 2. F is 50. L is 20 into 10 to the power minus 3. Now calculate it. So this part and this part will get cancelled. And 1000 upon 20 will be 50. So 50 ampere. So 50 ampere is the correct answer for this question. Hello students. So this particular question was asked from the power electronics section in your gate 24 EE. Okay. In this question, they're asking that in the DC to DC converter shown in the figure, the current through the inductor is continuous. Full stop. The switching frequency is 500 Hz. Okay. And the voltage V0 across the load is assumed to be constant and ripple free. Okay. So they have told me that it is a case of continuous conduction because the current through the inductor is continuous conduction case. Okay, they're asking you the peak inductor current. Okay, peak inductor current. So this is my inductor current actually. This is IL, inductor current, and they're asking about peak inductor current. I already told you guys that the peak inductor current is given as IL average plus, this is my IL average, and this was the case when the switch was on. Okay, and this is my time period here. This is my time period t. Okay, this was IL average. Okay, and it was a continuous conduction case. It was a continuous conduction case. So that will be the inductor current will start from here like this. Okay, and I know that my inductor average value is constant. Okay, this is my IL average, and this is the graph of IL, and this is T. Okay, so it is not getting zero because it is continuous conduction, and this was my delta I. Okay, so this is IL average. This is my IL average, and this part, if you see, it is delta IL by 2. So the peak current is this one only. So the peak current will be IL average plus delta IL by 2. Okay, so this was the inductor current in case of the boost chopper and buck chopper. So here the question is given for the boost chopper because L is here, switch is here, D is here, LST. So that means it is a boost chopper. Now in boost chopper, we know that the output voltage is given as V0 equal to Vs by 1 minus D. So V0 is 40 volt, as you can see here, and Vs is 20 volt by 1 minus D. So 1 minus D will be equal to 0.5. D will be equal to 0.5. Okay. Next thing is to calculate the value of this delta IL. Now I know that when the switch will be on, that is mod 1, when the switch is on, I know that my current will flow like this. Okay, it will be going through the inductor and then through the switch like this. So I can see that if I apply KVL in this particular loop, my Vs will be equal to VL, right? Vs equal to VL. So Vs is 20 volt and this is L, and delta I will be your delta IL, as you can see, that is from this point, which is your IL minimum. This is your IL minimum and this is your IL maximum. That is why the difference is IL minimum to IL maximum is going. So delta IL will be your change in the current, and this is occurring in the time interval T by 2. So delta IL by T by 2. Okay, VL we right now L di by dt. So di is change in the current. Change in the current is from minimum to maximum value. So IL maximum minus IL minimum is delta IL only. Okay, and the change in of time is T by 2. Okay, because this is T, this is your T by 2. So from here, I'll be able to calculate delta IL. So what is the delta IL you're getting? So it will be Vs T by 2L. So it is Vs by 2FL. So delta IL is coming out to be Vs by 2FL. Now just put down, put the values here. Put the values of Vs is 20 by 2, F is 50, F is 50 or 500, 500. F is 500. And what about L? L is how much? 2 millihenry, right? L is 2 millihenry. So this will be coming as So this 4 5 is 20, and this is 5 into 100, and this will become 10 square, 10 minus 10 to minus 1, so it will become 10 ampere. Okay, and I can also calculate IL average. See, IL average was equal to I naught in case of buck chopper, but for the boost chopper it is 1 minus D. Okay, so IL average was high in case of boost chopper. So I naught is how much I naught they have given? Achha, I naught you can calculate na from V naught by R. V naught is 40 and R is 10. So I naught will be V naught by R 1 minus D. Now just put the values. V naught is 40, R is 4, R is 10, R is 10 into 1 minus 0.5. So this is 4 and 4 by 0.5, that is 8 ampere. So therefore IL peak or IL max will be equal to IL average plus delta IL by 2. That is what I got from the graph. As you can see, for the continuous conduction mode, it is going from this to this. So this total part from here to here, you see that is IL maximum minus IL minimum, which is nothing but delta IL. So this is delta IL by 2 and this is delta IL by 2. Okay, and this part, this total part is your IL average. So if you just see here, this is your IL average and this part is your delta IL by 2. So IL peak is IL average plus delta IL by 2. So IL average is how much? 8 ampere plus 10 by 2. So 8 plus 5 is 13 ampere. So the answer of this question is 13 ampere. The peak inductor current is 13 ampere. So this waveform was drawn for the inductor current only. So this IL graph has been shown here, and from here I got the peak value. You can calculate the average value also, the peak value also. Okay, IL peak. You can calculate the IL minimum also, the minimum inductor current, maximum inductor current, average inductor current, all that you can calculate by just this, by using this graph or by drawing this graph. Okay.